everyone. We are starting our next session. The next session is by Akshit Tyagi. He will be speaking on Python and the Sun, transforming space science and open source. Sorry, with open source. Over to you.
Yep. I hope I'm audible. Thank you all for coming here today. I am Akshit, and right now I am a brief introduction about myself. I am in final year undergrad at JIT Noida, and aside from everything that final year undergrads do, I try to use my free time in contributing to open source and to projects that I like, projects that are at the intersections of all the interests that come along with the undergrad angst. So a more detailed view of some of my past, which could help see why I'm so interested about this sort of stuff. I got exposure to solar physics with Python via the Google Summer of Code program, where I was a student under Open Astronomy, and I got exposure to like open source and how open source as a philosophy is helpful in so many areas of life via volunteering at organizations like OSDC and FOSS United, and also helping out at PyCon India. It just once I understood the power of like communities and open source, I just couldn't help but be as much involved as I could be. So that's why I started volunteering. Met really awesome people. Some of you are also here today. I thank you so much for that. So here's a quick outline for the talk. I will be. I realized halfway through preparing that what I would be covering could be whiplashed because of there's some disconnected islands in my talk, and so I have laid them out like this. I will be covering why Python is so prominent in science, why it is useful in astronomy, and then I will go over solar physics. I would try to give an introduction to what solar physics looks like. I won't expect everyone to know what solar physics is about, because that was me 1 year ago, and that's everyone who touches grass probably. I will also be talking about open science, which I think is a very important thing that the general audience could know about. The people who care about open source, I think they can also really resonate with open science. So first of all, starting with how many of you have heard the term scientific Python before? I think yes. There have been awesome talks about it here as well. I see there was Agri's talk yesterday, and there's just so many talks. There's I think informally a complete track for that. So it's about how Python is useful in scientific communities. So how did we get here? How did Python become so prominent? Why was it a good choice in the first place? There are many reasons why. It's obviously very accessible. Python is has a very low barrier of entry, so the research oriented people can think about what they want to do with it instead of getting lost in syntax and all. But going beyond that, Python is very flexible. It has a vast ecosystem. People have been working out maintaining the project and extending the ecosystem for their own motivations, which extend way beyond science, and it is a really powerful thing for the scientific community to harness. And it's open source. Having open source tools in your research means that it is reproducible, whatever you do. That as much as your research is open source, someone else can take that work and build on top of it. They can extend it to how they see it, and that's why Python is a really good, really good advantage to the scientific community. And so those reasons also bled into the astronomy community. We had rapid adoption there. We had, AstroPy, the most popular astronomy package in Python, if I say so myself. And again, the advantages there also echoed why it was used in scientific software in the first place. Ease of use, extensive libraries, strong community support, all that. So here's what the AstroPython ecosystem has looked like over the years. There's have been these packages and these projects, they extend beyond just the packages. There have been AstroPy, AstroQuery, Stingray, SunPy. Some of these I've listed here, but obviously this is very much not an exhaustive list. Uh, though what I want to get at here is the existence of all these, packages, all these software has been a reflection of the open science movement. What is open science? It can be defined as a movement to make scientific research more accessible, more democratized, and make it available to every level of society. It promotes transparency, reproducibility, collaboration, and I intend to get on this more after I have shown SunPy, but in a way, it having all these packages available to you, you seeing that research is being done using all this, you get that feeling that I can do this as well if I have the motivations to do it, and in a way, you can become a scientist yourself. So we have open science to thank for that. Uh, Coming to my talk, which is where I'll be focusing on the sun. Uh, the best star ever, which is something I think a lot of you can relate to as well. Uh, Before going over, solar science, and I assume like you were interested in some astronomy or something of that sort, which is why you were interested in this talk. I would like to ask you to, venture a guess why we as humans study the sun so much. What's the need there? Does anyone have any guesses? Yes. Yup, exactly. The sun powers all life here, and our days and Mondays and hot weather and so much. But the sun is also a very stormy place. Uh, if you look at this image, this is an image taken by the Atmospheric Imaging Assembly on top of the SDO spacecrafts, one of the many satellites we have up there to take images of the sun. You can see these bright spirals of energy, these loops, glowing loops of plasma, like coronal loops. What this represents is that the sun is certainly not a very static thing. It's dynamic. It's already always in motion. Energy from the sun, like we can see here. In fact, we can actually not see this, which is why, like, when we look at the sun, we don't really see stuff like this, because this is beyond the visible wavelength for the human eye. So what I'm saying here is, under certain conditions, the magnetic energy of the sun, it can go out of control. It can get out of the sun and affect us on Earth. This is something that we see in solar flares or coronal mass ejections, or something just we call the solar wind. And this has effects on telecommunication, satellites, and all that. So here are two separate images of the sun. I want you to guess what's different between them, aside from the prominent color. Yeah, that's reaching there, yeah. But it's the same instrument. Yep, exactly. These are the sun being looked from different wavelengths. So one way of looking at the sun is that we look at it with different wavelengths, and different layers of the sun are information from different layers is captured by doing that. So when we look at the layers of the sun, the higher up we go, the hotter it gets. And the image on the left is 193 angstrom wavelength being captured, and on the right is 304. Both of these are from, again, the AIA, which was the image from before. So what this helps us is, see different behaviors in the sun. Like, so the one on the left, it is emission from the chromosphere. It one it tells us, about what the sun is like in relation to other objects. We can do this in and something in 211 wavelength as well, which would give us the magnetic fields. And if we overlay all of these, we can get really good looking images, which can also help us see uh, how this changes with time. And changing this with time also would give us an idea of how we can predict it going forward. And predicting it going forward is all the hype with the MLAI and predicting the future, making sure our astronauts don't go interstellar for no reason. Whoa. So first talk, and it's definitely an experience. So this is something that I wrote a quick script about, very last minute, might I add, to show a coronal mass ejection via sunpi. What this is you can see this is supposed to be the sun, and if you I have downloaded data in a 12-hour window, which on a date which was recorded as having a coronal mass ejection. So what you see here is the solar storm which was brewing at the sun's surface. The instrument here, if you are interested, is the LASCO written over there. It is on board the Solar and Heliosphere Observatory, which is an instrument out there again. So what this instrument in particular does is it uses white light images of the sun's corona, and we use it to observe CME. CMEs are masses. Coronal mass ejection says it does what it says on the tin. These are like mountains of mass being sent across space, and where the sun gets the energy for this, and how the magnetic storm of the sun goes with time is something that is very relevant to us on Earth, because if one of these is strong enough, it could knock out electricity. We could have blackouts and all that. And if they are not that strong, we can have very beautiful auroras. So we also have them to thank for that. So working with scientific software, especially in the solar physics area, looked like SolarSoft. And the first bullet is invisible here because that's how SolarSoft has kind of gotten. So there were lots of pain points there. It was written in IDL, and this is from research that I've done. Of course, I wasn't there when it was in all the hype, but from what I've gathered is that this is definitely IDL was proprietary and it was closed source, and SolarSoft in itself lacked versioning and it was difficult to get involved, and this is what led to the SunPy project. The SunPy project, I would like to to give a good definition. It is a community of scientists and software developers creating an ecosystem of Python packages. It extends beyond just a Python package and is now a whole ecosystem. It involves people, it involves initiatives that push the frontier for open science, open software in solar physics. So this began in 2011, and it began as a collaborative effort among solar physicists and software developers. Now this today is now a cornerstone project in solar physics research. You have people pushing out papers, you have people working on this, big organizations helping support the development of the SunPy project. So the core package what it does, it is again for solar data analysis. It helps you access data from different providers, read images, visualize, transform. So what it does is it offers you general purpose tools for working with solar data. It provides data structures that are useful for solar physics research, and then it also lets you access all the data providers like the virtual solar observatory or the HEK, uh, which are these organizations that host data for solar relevance. So the objective to state the mission of the project, it would be to develop and facilitate a high quality, easy to use, community-led FOSS solar data analysis environment. This is what I quote from the SciPy document because it's pretty important to quote it right. And the rate at which we are going forward in expanding solar technology or just space technology in general, the rate at which solar data will be generated and we would need to use it is only going to increase. And SunPy is definitely the front running and all powerful, all capable candidate to help us go forward with that. SunPy affiliated packages are these projects that perform more specialized tasks that were sometimes initially part of the core package, but they grew out into more their own packages because the scope of them would just start differing. There's some of these that I've mentioned here. There's SunKit Image, NDCube, DRMS. There's also AI API, an entire package dedicated to the atmospheric imaging assembly, those images of the sun that we saw before. So SunPy's impact, very, very impactful. It has been used in numerous scientific publications and pretty well recognized throughout the scientific community. I would now like to give a quick tour of the technicalities of how SunPy looks like. So the SunPy package, for an overview, it has units, times, coordinates, maps, time series. These are the basic building blocks for doing astronomy and just solar research with Python. Units, SunPy is always explicit about what quantities go into each function and what returns out from them, so that we don't lose marks for not writing units in exams. So it uses AstroPy's quantity objects. This is again a powerful point for SunPy because it is building upon an already existing ecosystem instead of having a closed off world of its own. It is something that you can plug in with other features. You can, something that benefits AstroPy quantities can benefit SunPy quantities. So working with units looks like this. You just use AstroPy's units as imported. You can give it a certain length, or you can give it whatever physical quantity you want that's supported yet, of course. After units, the next basic thing which you will be working with is time ranges. It is pretty straightforward as well. They are implemented via a parse time, a very helpful parse time function where you can convert strings to time objects and vice versa. So this is a step above, and what I personally really like about the project, the acquiring solar data side of it. So like I said before, you can get solar data right from the Python package. You don't need to get it from somewhere else, convert it to formats that would work well or something like that. You can use Fido. Fido is this SunPy's unified downloader. What I mean by that is, so there are instruments out there in space. They capture data from the sun. We don't query them directly. They query it back at Earth to whatever institutions that are hosting them, that are supporting them. So they host this data, and what Fido does is it provides a single interface for you to query all that all those different data providers back on Earth. So to acquire solar data, you would typically import FIDO. You would import attrs. Attrs are data structures for FIDO attributes. The search query looks pretty simple. As you can see, you typically send a start time and an end time. You send which instrument you want to query, and you send what wavelength you want to look at, or something else which is unique to that instrument. And you get all this data as a pandas derived AstroPy query result table. What this is not the data itself in its entirety. This is just the metadata for now. You can now do intersections with this with some other results. You can then, like, once you are certain that this is the data that is relevant for your work, you can then start downloading it, because these are big files. These take a lot of data and a lot of time to download, of course, and a lot of resources. But yes, FIDO in itself is very extensible. Like I said, that earlier we were using it to download AIA images like before. Now we can use it to query for solar flares. We can do this by querying the HEK. The HEK hosts a whole vast array of different solar event information, and this is how you can do it for flares. After that, you can add sources by yourself. You can extend it by yourself for other organizations that may not have this support yet. In fact, this is something that has seen a lot of work in recent SunPy development, and in the next release we will be having this merged in, which would change the scraper API and change how you want to add these clients. But the point here was just simple. You only need to subclass some class from the SunPy code base, and you can have a lot of powerful benefit and value out of it. You can plot solar maps directly in SunPy as well. This is an example of using an inbuilt AIA image, because again, these are very big files. And then solar work that usually gets done with these images can get really, really hardcore, and it would be quite an undertaking to cover that properly. So this is one of the more approachable examples where we could find bright images on the sun's surface. And I hope this gives an idea of how visually research can be done using Python software. So again, this was like, I saw this around 2 years ago, and I was like, this is pretty hardcore stuff. Good job, guys. I don't think I would be able to get involved, but I applaud your efforts. But if you feel similar, like if you think that this is out of reach or something, especially if you're a college student like me, you are dead wrong. You can help out the project in many ways. You can use it. You can come over if you want to develop it going forward. You can contribute to it. The community is really nice, which was probably the biggest factor why I personally could I personally stayed and could be consistent with my efforts. You can contribute in many ways, like in a standard open source project manner. You can contribute documentation, you can contribute code, or you can just use this for your own citizen scientific endeavors, and then provide valuable feedback, something that you would like to see, something you would want to add going forward. Now, remember I mentioned about open science before, and I said that I wanted to, look at SunPy as an example for that open science aspect. So open science, the movement, can be, can be very well represented by these fair principles. These fair principles state that for promoting open science, these projects, your research should be findable, it should be accessible, it should be interoperable, it should be reproducible. So we saw all that with SunPy. You can find SunPy very easily. You have it on the Python packaging index. It is accessible. Everyone can download it. It's not like you need some specific credentials from some research institute, and only then you can access all the capabilities that it offers you. It is interoperable, like AstroPy units. It's very well integrated within the system. You don't have to be in a particular bubble to be able to use it. It is reproducible. I do something in SunPy, I can send that over to you. You can do it as well. This open science, I think, is best understood with contrast to closed science. Closed science is something, I did some work, and I could be wrong here, I could be right, but you would not be able to so readily check my research if it, say, involves a lot of resources. There have been cases in the past where just because of the amount of resources some study took, it was like 8 years later when somebody else did that as well, and then they were able to find some hidden biases or something that went wrong before. Closed science also, has that thing where if I did work in this field, now I have all this data with me, all this technology with me, which can help me go forward here, which provides me an advantage, I guess, over other researchers. But what doing it openly means is you are, distributing that knowledge freely and just promoting collaboration and stuff like that. The practices for open science are, again, like open access, open data, open source. Open science, I won't say that open science is like, applicable everywhere. Of course, there's places where it needs to be closed off, like some data which should be kept secret, but open science in general advocates for democratizing science, that everyone should have access to science. It should not be gate kept. So open source software, like SunPy, they have had a big impact on open science. They enable, reproducible research. They make sure that research can be verified and replicated. By sharing code and tools, the scientific community can build upon each other's work, leading to faster advancements and participations from all levels of society. There are many initiatives that help further this goal. There's open astronomy. This is specific to kind of astronomy projects, but it is still a very, very wonderful initiative. There's also Pi Open Sci. I think they started out a couple of years ago, and they have a lot of benefits for projects that are going forward for the open science in Python. They offer an open peer review for Python software. They also offer benefits, like they have a tie-up with the Journal of Open Source Software, I guess, where the PyOpenSci peer review would be accepted as a JOS review and could get published there. I think just closing off, I would say that there are challenges in open science, and which are again balancing openness with where things should not be open, and ensuring long-term stability, and just promoting it in educational institutions and all that. There's these relevant links. I would very much recommend to check out the Transform to Open Science program by NASA. They offer training in open science fundamentals and technical abilities. Thank you so much. That was it. I hope it was worth your time and you got something out of it. And again, thanks for Thanks for coming to the talk, and I hope you have a wonderful PyCon India. Happy Sunday.
Thank you so much, Akshit.